All right. So today we are going to talk about waves again. So there was one simulation where with your slinky, you had to send a wave down your slinky. Let's do this. Read. Schema. On the ground is better. Okay, so send a transverse wave. Ah, do you see what happened? You can stand up. Okay, watch the wave after it contacts, like, at my end. Okay. What happened? It went back to him. Why? Ugh, it's kind of fun, actually, isn't it? Okay?
Yep.
So, it's like each of our hands are a fixed end. Okay, it's like it's staying there. Okay, it's not an open-ended spring. So when you send a wave down the spring and it hits a fixed end, that energy is still there. It's just transferred and goes back the other way. Okay, so it's still the transfer of energy throughout the spring. Turn in your textbooks, page 417. Page 417. And we are going to read standing waves in a fixed spring. So what we were doing was a fixed spring. When you generate a wave train, so just the wave energy, in a spring that is fixed at one end, the reflected wave train must pass back through the incident wave train. These two wave trains have identical wavelengths and nearly identical amplitudes. There might be some energy lost. That's why there wouldn't be the same amplitude, because think amplitude equals energy. Okay? For incident and reflected wave trains, the initial point of contact is by definition the fixed point at which the reflection occurs. So basically, fancy way of saying, right, the energy is transferred and goes back along the same medium. And it should be an identical wave, but the reason why it dissipates is because it loses energy, right? And that lost energy will eventually, then there will be no wave. So you have to keep putting the energy into it. So now, what we're going to be focusing on today is something called a standing wave. So if you can get that wave moving to a point where when it is reflected back, those two waves are like identical. And they do kind of an overlap, just like we did yesterday, where you have two waves, and if they're the exact same, they'll overlap, it'll double, or it will start to actually resonate. Okay? So, yeah, I should just start the basic lesson, and also I'll just keep going. So we're talking about standing waves, and that's all about the wave being reflected back after a fixed point. Okay, when two waves with identical wavelengths and amplitudes move through each other, the resulting interference pattern can be explained by the principle of superposition. That's what we did yesterday. So that's just a recap of the principle of superposition. How do these two waves interact with each other? When waves are when waves are in phase, so in phase, I would just kind of underline that, in phase, the constructive interference occurs, and when the waves are out of phase, destructive interference occurs. So that was what we did yesterday. Now, so this is something new. This is new now. When two waves pass through each other in opposite directions, they continually shift in and out of phase to produce a wave that seems to oscillate or vibrate between fixed points rather than moving through the medium. This is known as a standing wave. So it appears like the wave is not actually, that the energy is not actually moving, that it just stays the exact same wave. So it looks like there's no energy transfer, but there still is, but it just looks all the same. So here, we don't have it in color, but this one coming in up to point A is, we would say that's VB, or velocity of B. And then this side up to point A is VA. So this is wave A, and this is wave B. So it's like, say this is me and Reed holding the slinkies at each end. And if we got it going, well, and what actually would work, which I'm going to try and get, is a long spring, like this, except really long, and you get it going, and then you can make a standing wave. I'll show you a video of it. I'm going to try and get the actual materials so that we can do it. So they're not, it's not like they're crashing into one another. They just continue to make this constructive interference. So here are A, this is waves A plus B being combined together, and now I have constructive interference where they actually get bigger. At places where there's destructive interference, it would level off. So the resultant standing wave is actually going up and down, up and down, up and down. Now, I'll show you a video of this, so then you can kind of visualize it a little easier. Actually, I'll show you this one first. Okay. So they have that spring coil thing that I showed you, and
result of reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down on itself. If I send a rhythmic pulse, it reflects on itself. This is the fundamental mode.
okay, so it reflects on itself. Okay, that's the key.
Sending the pulse at twice the frequency results in the second harmonic.
So it looks like that wave is almost just standing there, like this one wave right here just goes up and down, up and down, up and down. This one just goes up and down, up and down, up and down. Right here, it appears like there's no movement, right? Or no transfer of energy, so no movement, no movement, no movement. That's what it appears as. Those are the nodes, and then these are the waves moving. So the first one, where it was just like this, that was called fundamental frequency, okay, where it is reflected back on itself once. Now watch and listen and hear what he calls this next one.
If I triple the frequency,
Maybe he didn't say it.
if I triple the frequency, I get the third harmonic.
So each one is like second harmonic, third harmonic. So now there's more points of nodes. So right here and here, that's where it appears to be not moving. Those are the nodes, okay? Now here's another good one. This is a little bit longer, but it's really, really good.
What we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, let's go higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it...
So this is like when beats are happening. It's not a consistent constructive. It's inconsistent.
Here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working.
You can even touch it and it keeps
So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera.
So the first one was the
So
fundamental.
here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice, this is a node, this is a node, and the middle is a node. So we have three nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5.
So that's the fundamental frequency.
And there we go.
It almost reminds you like of a skipping rope.
It's basically the scenario of a jump rope. Now, I can find any of the other, all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was that around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 1/2. 1 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high-speed camera and verify for yourself that it is 1 1/2 wavelengths.
So remember, a wavelength is defined from the same point to another point. So say we picked like, this is one point, and we go down and up and back down. That's one wavelength, and then plus another half.
So again, third harmonic, 1 1/2 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
Okay. So I wanted to show you this actually live. If I can get the materials, we will still do these things together. But does that kind of help visualize what a standing wave is. So it's always about a wave that is reflected back on itself at a certain frequency to actually produce a standing wave. So that its reflection is the exact equal as the wave that was produced. It's kind of cool. So as you saw in the video, we have certain definitions